Well, hello and good afternoon, everyone. Thank you for joining Geoscience BC's Energy Resources webinar. My name's Gavin C. Jerome, and I'm the President and CEO of Geoscience BC. I wish to acknowledge at this point that our board chair, Lana Eagle, is not presently able to join us, but she may join us later through the webinar. And I also want to thank Lana for her ongoing contributions, steadfast supporter and volunteer of Geoscience BC and our current board chair of Geoscience BC. Now, before we continue, note that we've scheduled time for you to ask questions following each technical presentation. So feel free to submit questions using the chat function or use the raise hand feature if you would like to ask a question directly. And to minimize background noise, if your microphones and cameras have been turned off, and we will invite you to turn them on during the question periods. Please also note that today's webinar is being recorded, and a recording of the session along with the presentation materials will be shared with everyone following the webinar. A little bit about Geoscience BC. It was founded in 2005, and since then we've built a strong legacy based on scientific excellence, collaboration, and public service. In fact, over the past 2 decades, we've completed 85 energy, water, and geothermal research projects. This work has contributed significantly to British Columbia's and to Canada's ability to develop safe, reliable, and responsible energy resources. And Geoscience BC's high quality, and I would offer pragmatic research projects continue to provide important benefits by improving our shared understanding of economic resource opportunities, while helping to identify, assess, and mitigate potential environmental and social impacts. A key factor in Geoscience BC's success has been our collaborative model, bringing together industry, government, Indigenous partners, academia, communities, and a very dedicated network of subject matter experts and volunteers who are committed to rigorous, peer-reviewed, and publicly available science. Our first technical presentation will be delivered by Dr. Brad Hayes, and our second technical presentation will be delivered by Dr. Kathy Hickson. Now, before we begin our technical presentations, I would like to acknowledge and thank ResourceWorks for sponsoring today's Energy Resources webinar, and to introduce Stuart Muir, who is the President and CEO of ResourceWorks. Stuart is a widely respected communicator specializing in energy, natural resources, and public policy. As a founder of ResourceWorks, he leads a national organization dedicated to improving public understanding of the role that responsible resource development plays in economic prosperity, environmental stewardship, and Indigenous partnership. So with that, I'll turn it over to you. Thank you, Stuart.
Thanks, Gavin. Thanks to Lana, and I hope she is able to show up later on. Your leadership has made this project possible. I've had the pleasure to work with you all from the board, from the organization over many years. So impressed by what you do. Thanks everyone for being here today. This is a valuable use of your time, in my opinion. At ResourceWorks, our mission is to help British Columbians and Canadians better understand the role that natural resources play in their lives, their economy, their future. And we believe that mission starts with a simple belief that good decisions require good information. And that's one reason ResourceWorks and my board here is pleased to support the webinar today. The public conversation about energy often focuses on projects, on policies, on regulations, on markets. That's what the public hears about. But all of those things ultimately depend on something more fundamental, and that is a clear understanding of the resource itself, which I think is where Geoscience BC has played such a unique and important role. It's a space between other functions, navigating a journey. It's between academic research, public policy, commercial development, regulation. It's not advocating for projects. It's not enforcing rules. It's not pursuing science for its own sake, but it's generating practical knowledge that reduces uncertainty and helps British Columbia residents make informed decisions about stewardship, development of their natural resource inheritance. And because BC is fortunate to possess extraordinary energy resources, in particular realizing the benefits of responsible development requires trusted information, rigorous analysis, and a commitment to understanding opportunities and impacts too. So Geoscience BC has built an impressive record of providing that kind of public value. I don't see anyone else doing the unique role that they have. Its work helps communities better understand their choices. They've helped Indigenous nations all over the place evaluate opportunities. They've helped governments make better policy and help industry make better decisions. We've seen all that in action. So at this time in 2026 is a world where energy security, economic resilience, responsible resource development, all of these are converging and never have been so important. And that's why I think this is such a great discussion today. So on behalf of ResourceWorks, thank you, Geoscience BC, for your unique, valuable work. Thanks everyone for participating. I'm looking forward to being here to hear the presentations. And now back to you, Gavin.
Thank you, Stuart. Really do appreciate that. Very insightful remarks, and it really helps to set the context for today's webinar. And again, thank you to you and ResourceWorks for your support of Geoscience BC. So now let's welcome Dr. Brad Hayes. Brad is the Senior Geoscience Advisor with GLJ Limited, one of Canada's leading energy consulting firms. As a geoscience expert in his field, Brad has been directly involved in many of Geoscience BC's most influential energy research projects. And today, Brad will mostly discuss natural gas development in northeastern British Columbia and highlight how BC projects improve our understanding of water resources, reduce seismicity, and greenhouse gas emissions in the region. So with that, over to you, Brad.
Great. Thank you very much, Gavin. Pleasure to be here today. Let me do the screen share thing here. Okay, hope everyone can see. So yes, as Gavin said, I'm happy to review some of the many projects that Geoscience BC has been involved in facilitating upstream natural gas development in northeastern BC. And as I'll introduce in a minute, what you'll see is our work has been not so much on the resource identification side of things, which of course the operating companies are most interested in terms of putting things together, but we're very busy in understanding the supporting roles, environmental issues. How do we actually clear the way for these projects to happen in a safe and sustainable fashion? So let me go, here we go. So just to introduce the topic, I think we all know that we've got massive natural gas resources in British Columbia. They've been produced since the 1950s to domestic markets and the US, but more recently with the startup of LNG Canada and the other liquefied natural gas projects that are under construction, gas production is rapidly expanding. And that expansion is fueled by unconventional gas reservoirs that require horizontal drilling and hydraulic fracturing in order to produce enough gas quickly enough and economically enough to feed our growing demand. So we've known about the presence of unconventional gas reservoirs in northeastern BC since the early 2000s. And there was quite a lot of work, particularly within industry, within academia. The Ministry of Energy, Mines and Petroleum Resources, as it was known at the time, and the Geological Survey of Canada have all contributed a great deal towards understanding where those unconventional gas reservoirs are, what their nature is, and how to best exploit them. The key roles that Geoscience BC has played in developing the resources is by characterizing and understanding associated environmental issues so that natural gas development can move forward with minimal environmental issues and mitigating those issues that do occur. And just as a reminder to us all, the horizontal drilling, hydraulic fracturing methodology that's used, this is just a kind of a standard diagram, but Up until 2000 or so, we drilled vertical well bores from the surface down to gas reservoirs, produced them from those vertical well bores. The introduction of the technology, lots of different engineering advances to take those well bores horizontal at depth. Here we're talking about a reservoir that's perhaps 2,000 meters deep, so thousands of meters below our shallow groundwater and potable groundwater up there. Turn that wellbore horizontal, and then inject pressure and water and supporting chemicals into it to fracture the reservoir that allows economic production of gas from rocks that would not otherwise be able to produce at all. We built on decades of conventional exploration development in the Western Canada Sedimentary Basin, including in Northeast BC, to understand where these reservoirs are and how we might develop them. And just in a little bit more detail then, here's a map of British Columbia. The colored areas on the right are the sedimentary basins, northeastern British Columbia in particular. The rest of the province is more in the mineral side of things. But in northeastern BC, we've got three major unconventional gas basins: the Horn River Basin up here, and it was assessed at having about 78 trillion cubic feet of marketable gas resources. And just for a point of comparison, right now, Canada produces about 7 trillion cubic feet annually across the entire country. So that's an enormous resource compared to our current production. The Liard Basin to the west of Horn River is an even larger resource, assessed at 219 trillion cubic feet of marketable gas. But the big granddaddy of them all is the Montney Formation. This estimate is over a decade old, 449 TCF, and I think probably if we really looked hard at it today in light of continuing evolution of the horizontal drilling hydraulic fracturing technologies, that we would see that resource is probably even bigger. But the Montney is the resource that is fueling most of the production from BC today, including production to LNG. We've got so much gas coming out of that area that our big resources to the north in the Horn River and the Liard have not been exploited nearly as much, but they remain there ready to go. So the environmental issues that we have to deal with when we're producing natural gas from unconventional reservoirs, there are three major issues that are associated with the subsurface and geoscience that Geoscience BC addresses. And those are protecting water resources, reducing and mitigating induced seismicity, and reducing net greenhouse gas emissions. So what I want to do is address each of these issues in turn and point out 2 or 3 projects that Geoscience BC has completed in order to address those particular environmental issues and explain how they've helped industry advance. So in talking about protecting our water resources, well, hydraulic fracturing uses very large quantities of water in order to stimulate the production, to pump water downhole, to help fracture the rocks, to help produce those fairways that gas can flow up through. So this is a typical surface operation. You've got water stored in big tanks or sea rings. They are transported, that water is transported to the wellbore and pumped down under high pressure to fracture the rocks. So the fact that we use so much water raises some issues. If we're using water that comes from rivers, lakes, or streams, then we face the potential of depleting potable or drinkable water resources. When the well has been fractured and we allow it to flow back and start producing gas, it also flows back some amount of water as well, and that water can be contaminated with naturally occurring substances that we find down in the reservoirs underground. When that does flow back, we also have to be very cognizant of the fact that we cannot allow surface water to be contaminated by either those flowback operations or by just the operations at the well site. So these are the issues that Geoscience BC has looked at addressing. So in terms of mitigating depleting potable water resources, Geoscience BC has undertaken programs to characterize surface and shallow groundwaters to understand what our water resources are, what kind of quantities of them move through the environment, and just provide basically a background for understanding what surface water we might be able to use safely. A key issue, and one that I've been involved with a lot, is to characterize deep saline aquifers. Those are rock formations that are considerably deeper below shallow groundwater. They naturally contain non-drinkable or non-potable saline waters that can actually be good sources of water for hydraulic fracturing and great disposal zones. Similarly, when we have that flow back water come back up the wellbore, we need to safely dispose of it, and deep saline aquifers are a place to go. We don't want to contaminate surface waters. If we can basically re-inject saline groundwater back into the ground about where it came from, then we've got a win-win situation. Contamination of surface water is the third issue that we addressed. Now, there are a lot of very good regulations that the BC Energy Regulator directs operators to follow in order to prevent any of their operations from contaminating surface waters. So I'm not going to talk about that so much, but let me talk about the first two here. So in protecting our water resources, to characterize surface waters, again, to understand where the water comes from, how much there is, how it flows through the environment. One of the projects that Geoscience BC undertook a few years ago was called the Peace Project. And it was a multi-targeted type of project where Geoscience BC had separate teams that did aquifer mapping and shallow groundwater, so understanding where our groundwater occurred in shallow horizons. We mapped the shallow bedrock in water wells and gas wells to, again, better understand what sort of shallow section was available for water to flow through. And then the Peace Project also included airborne geophysical surveys to help characterize the shallow subsurface. So in mapping groundwater aquifers, there's a lot of work that we could do at the surface to understand the distribution of sedimentary rock, or actually sediment bodies. And this is a picture from a very gravelly stream deposit associated with glaciation several thousand years ago. And as you can imagine, just looking at these very coarse-grained gravels, this is a great conduit or aquifer for groundwater to flow through. So very important to understand where these types of aquifers occur, and we can map them in outcrop. We can also use data from water wells and from gas wells. We've got data that we collect as we drill the wells, and all the black dots on the map here are wells that we used in this characterization idea. And again, what we wanted to do was to understand the distribution of capacity to flow water or capacity to hold back water in shallow bedrock. And both these mapping projects were supported by running airborne geophysical surveys, where it flew electronic receivers over top of the surface here, and we're able to map out various geophysical parameters. Here, these are resistivity measurements in the subsurface, and interpreting these resistivities showed us where some of the major water bodies were that flowed through in the groundwater through the subsurface. And so a multi-pronged, multi-task approach to understanding shallow groundwater and how best to use it and to protect it. I mentioned deep saline aquifers. This little cartoon goes back to around 2008 or 2009, our first big project in the Horn River Basin in trying to understand deep saline aquifers there. So kind of, here's a schematic geological section. Our shale gas reservoir was down here about 2,500 meters deep. So there's one of our vertical well bores turned horizontal. But what we're able to map from well data was the presence of a shallow aquifer, relatively shallow, about 500 to 700 meters deep, where there is very, very high reservoir quality. It would flow water very rapidly, but the waters were they're quite brackish. They're not usable for any industrial or human consumption use, but what they were extremely useful for as source water for hydraulic fracturing and as a disposal zone for that flow back water that came back up after the fracturing. So it was a great deal. It was a very successful project in understanding how we could use deep aquifers to protect surface water resources. one thing that was interesting about it was this is just a map of the thickness of those deep saline aquifers in the Horn River Basin. And you could see right away, just by the characteristics of things, there's kind of a background of capacity available, but some areas, those aquifers are very thick and very high quality. And in fact, some of those areas, such as in the orange and red highlights here, became favored development areas for operators because they knew that they could more quickly, efficiently, and cheaply dispose of their flowback waters and source frac waters. So it's highly useful work in supporting unconventional gas development while mitigating environmental issues. The second topic to address, mitigating induced seismicity. So it's a bit of background with this cartoon here that I borrowed from the University of Calgary. Just about any time that we inject water into the subsurface, whether it's through drilling a horizontal well and fracturing it, whether it's through simply injecting wastewater to dispose of it, or whether you're even doing things like geothermal, where you regularly pump water in and allow water to come back out again. And Catherine's going to tell you something much more sophisticated than that. But the key here is that anytime you undertake these activities in the subsurface, if you're in a terrain such as we are in northeastern BC, where there are pre-existing stresses associated with mountain building and faults or natural breaks, planes of movement within the rock column, if you inject fluids very close to that, you can change pressure regimes, you can inject fluid actually into faults to help facilitate movement along there. What can happen is that fluid injection can result in a induced seismicity or a small earthquake. And of course, there are obvious issues around that, public safety concerns if there are earthquakes, and damage to existing infrastructure. So Geoscience BC projects that were designed to mitigate induced seismicity were threefold here, I've mentioned, assessing the actual operational risks around hydraulic fracturing. So actually comparing the records of induced seismicity to frac operations to understand how they occurred. We have done quite a lot of work at characterizing the suitability of deep aquifers, some of those same deep saline aquifers, to understand what their capacity is for safe wastewater disposal without inducing seismicity. And then there was it was a very interesting project where we assess the shallow geology to understand susceptibility to seismic amplification. In other words, depending on the nature of the ground that you're standing on, you can feel a seismic event to a greater extent or to a lesser extent, depending on the characteristics of the shallow geology. So we could identify areas that were more at risk for induced seismicity than other areas. So one of the projects referenced here, here we are in the Fort St. John area. The triangles are grids or locations of seismic recording stations, and the red dots are all different seismic events that were recorded to happen in the subsurface, most of them associated with either hydraulic fracturing or with wastewater injection. Now, these are very small. For the most part, very few of these seismic events are sufficiently large to be felt by the public at the surface, but they can be picked up by the monitoring equipment. And with the working with the records of what's actually happening at well site operations at the time that seismic events are induced, then we can understand a bit more about why that induced seismicity occurs. What are the geological factors? Where are the faults? Where are the other characteristics of rocks that might facilitate a movement? And we want to understand completion practices. Would we get more seismicity, for example, if we injected water faster at higher pressures? Total volumes, length of the wellbore, things like that. So there's a lot of work done to understand how hydraulic fracturing would affect seismicity, and recommendations made to modify hydraulic fracturing programs so that the risk of new seismicity would be lower. Another one of the major efforts we made at Geoscience BC was to study the major disposal zones, or the deep saline aquifers into which water was being injected. So even before hydraulic fracturing started, there were wastewater operations around where operators would inject wastewater into these aquifers that are 1,000 or 1,200 or 2,000 meters deep. And so the blue dots here are a lot of well site locations where injection occurs. This particular map is one of our deep saline aquifers, the Catamount Formation, and the colors and contours simply indicate the thickness and reservoir quality there. So again, what we want to understand is a few things. What's the capacity of these reservoirs? How are they going to perform? What are the geomechanical or stress regime in there that will influence how they might break or fracture? Understand the major structural elements, such as the front of the foothills here, that would change how these rocks might behave when you inject fluids into them. So again, the goal being to look at the behavior of disposal wells as water was disposed into them over time, relate them to the characteristics of the subsurface reservoirs, and come up with guidelines and recommendations about how much water can we inject, where should we go to stay away from hazard zones such as faults and things like that. Just a lot better understanding of the best places to go and the best practices to follow so that induced seismicity isn't a big issue. The third issue, just want to address quickly here, is the reduction of greenhouse gas emissions. So not only natural gas development, but lots of other industries as well, such as pipelines, as forestry industries, as some agricultural practices, they emit greenhouse gases, particularly carbon dioxide. And this is a map from one of Geoscience BC's projects in northeastern BC. It just maps out all of the big point sources of CO2. So we've got a refinery down in Prince George. We've got a number of gas plants. We've got compressor stations, things like that. Anywhere that's burning fuels to generate CO2. So there's quite a bit of it around, but all of these point sources emit a fair bit of CO2 in relatively pure form. So that these are the places we might want to go to capture carbon dioxide, transport it somewhere, and inject it safely underground. That's carbon capture and storage. The Northeast BC Geological Carbon Capture and Storage Atlas was completed a few years ago by Geoscience BC, and the goal there was to, looking at some of these same reservoirs that we dispose water into, look at their characteristics, understand where we have the best capacity to inject CO2, where we know it can go into a reservoir and will stay underground. It won't leak out, and it'll be stored there in perpetuity. Now, a lot of our understanding of how much capacity is in the subsurface relates to where we've already got a lot of well control. So most of the wells in northeastern BC are drilled in Peace River country, and you can see here we've actually been able to identify some really hot areas, a lot of capacity for CO2 storage in the Peace River block here. Also up near Fort Nelson, where there's major gas development 60 years ago or so in the Clark Lake field. And again, we see a lot of capacity to store CO2 in that depleted gas reservoir up at Clark Lake. So we can match up the locations of the emitters and the locations of these disposal reservoirs to try to decide where is the best place to build a capture facility and where's the best locations to pipe that CO2 to, so that we can inject them safely into the subsurface. Now, just to finish off here, not every Geoscience BC project meets or results in great success. I can say that because my firm did this project, so nobody can argue with me about it. But we looked, in this case, at the Nechako Basin in central BC. So it was south of the area that we saw mapped before, and Prince George is just off to the north side of there. We've got Williams Lake over here. Just from the look of the surface map of the geology, you can see it's a very, very complex area. The sedimentary basins are relatively small. They're very poorly understood. We don't have very much data. We've listed little tags for all of the wells that are actually in the area. So there's only about a dozen or so, and a few seismic lines. And so with the lack of data and with the complex geology, we're able to identify only very small capacity for carbon storage and very high risk capacity. We really didn't know from the data that we were able to gather whether or not a CO2 injection project would work in this area. But even with that, if you want to call it a negative result, it provided a good guideline for planners and regulators to say, well, okay, if CCS is going to be a strategy that we want to follow to reduce net emissions, we better be doing it in a place like northeastern BC versus trying in central BC, where the geological conditions were just far less favorable. So to sum up then, Geoscience BC has engaged with industry and academics to better understand the key environmental risks around natural gas development, focused on water resources, induced seismicity, greenhouse gas emissions. And so this research has been used to actually guide industry in their practices, regulators in understanding what regulations are reasonable and can be expected, that the operators can follow them, and policymakers in terms of understanding the realities of how much CCUS, for example, can we do, or how much can we mitigate or reduce induced seismicity. So that's been an extremely brief look at some of the many projects that Geoscience BC has done to support natural gas development, and I think that these will continue to be extremely useful in the future. Well, thank you.
Excellent. Thank you, Brad. Your presentation was fantastic, and I also want to just reflect on some of the comments that you made. A lot of the materials that were just conveyed to you really demonstrate the quality of the work and the results that can be positive in many cases in order to further where it makes sense for resource development to happen. But it also shows where you need to do the science in order to determine where resource development or other initiatives may not be a good idea given the complex geology in British Columbia. So that's much appreciated to reflect on that, Brad. And to everybody on the audience here, just note that we have posted many of the projects that Brad referred to in the chat, and there's a lot of information there. And if you haven't clicked on them or dug into them, please do. There's lots of good data and information over the last, again, over 20 years of activity and quality work being done. So with that, we do have an opportunity now to ask Brad some questions. So I'll open it up to the audience here. I'll look to the chat if you have some questions, or raise your hand, and I'll see if I can find you amongst the many here to ask Dr. Brad Hayes a question about the presentation he just provided. Just looking for that right now, and I'll maybe just get started with one opening question, especially given some of the context where we find ourselves, in Western Canada and North America and so forth. And it's really just helping better understand the plays or the unconventional gas opportunities in Northeast BC, Brad, relative to the big U.S. Shale plays. Like the Marcellus and the Permian Basin and so forth. So maybe you could help us just better understand the scale and scope of what we see in Northeast BC versus some of the U.S. plays.
Yeah, and I see a question in the chat that's along the same line, so that's good. We can address two at once. The Montney in particular we use this term too much, but it is a world-class unconventional play. The resources there are comparable to the best of the U.S. unconventional shale resources, including the Marcellus and the Permian Basin. The Montney covers a very large area. It's very thick. Its characteristics are very well, accessed by modern horizontal drilling and hydraulic fracturing. The scope of the gas resources is comparable to even some of the biggest fields like offshore Qatar, where they're producing from a conventional reservoir. Nevertheless, the scope or the availability of the gas is quite similar. So we've got, we could produce just from the Montney for decades at our current rates or even elevated rates. And after that, there's the Horn River and the Liard are available. And if you want to even go outside of British Columbia, go further north into the Yukon and the Northwest Territories, there are similar shale unconventional plays as well.
Thank you, Brad. There is a question here, an interesting one about, it's probably a calculated, experienced guesstimate, but how many years could we supply the EU with our resources? Do you have a sense of the scale and scope of that?
I think the limitation there is far more the number of facilities we can build to do the transportation. We can say 449 trillion cubic feet of gas available to market from the Montney. I think if we got to the point where we could ship, I don't know, say 2 or 3 trillion cubic feet of that gas overseas every year, we'd be really happy. So could do the math on that and come up with 150 years. So yeah, a very long time. The constraint there is not in the resource that we've got. The constraint is how we can deliver it. I see, I'm just looking, Gavin, at a couple of the questions on the chat here. So one person asks, has water recycling been considered for fracking water? And yes, British Columbia is probably, I think, the most advanced jurisdiction in terms of water recycling. The regulator has set up regulations to allow operators that are working in an area where they know they're going to be drilling a lot of wells. They can set up central water facilities and they can recycle the flowback water and filter it and use it again, and they trade water amongst operators and things like that. So there's actually been a very dramatic decrease in the total water consumption by the hydraulic fracturing industry in northeastern BC because of very efficient recycling. And I don't fully understand this, and I'm not totally up to date, but I don't think Alberta's regulations are nearly as encouraging towards recycling.
Thanks, Brad. Maybe we can turn to the question. There's one here from Jose Condor, and then I see a hand up also from Katie O'Neill. So perhaps we do those two next.
So sorry, are we looking at the?
And the question from Jose Condor is how much disposal and storage capacity is left in Northeast BC, and are we running out? And what studies should we focus on first?
Well, I think the studies we've done to date identify a lot of potential. I think if I remember correctly, that carbon storage assessment said 4.2 gigatons or 4.2 billion tons of storage capacity in the reservoirs that they studied. So right now in Canada, we're, I got this right, I think we're storing about 3 or 4 megatons per year. So again, we could be pumping, we could be storing CO2 in northeastern BC for decades at the rate that we're extracting CO2 right now. In reality, if we're going to make a material difference in overall net emissions, we're going to have to really step up on the amount of carbon dioxide that we store. But nevertheless, again, the kind of like the last question, it's the infrastructure that's more the limitation than the actual capacity itself.
Right, that makes sense. Thanks, Brad. In interest of time, why don't we do this maybe last question here from Katie O'Neill. I'll open it up for her to, I believe, just verbally ask the question. I don't see it in the chat, so 1 second here.
Awesome. Are you able to hear me okay there, Kev? Awesome, thank you. So, apologies, I wasn't able to get the chat working, so I appreciate you taking my call. or taking my question. Appreciate the information very much as well. Just wondering, if so, I'm with an organization called Carbon Removal Canada. We look at sort of advocacy and research around direct air capture and bioenergy with carbon capture projects, things like that. And we're thinking a lot about carbon mineralization as a storage pathway. And so I wanted to ask the question if that's something that is sort of on the radar of Geoscience BC, and what you think that potential might look like.
I believe there, with respect to carbon mineralization, then instead of just injecting carbon dioxide into pore spaces and sedimentary rocks and keeping it in the pores, the idea of carbon mineralization is to inject carbon dioxide into fractured rocks with certain chemical compositions, such that you'll combine the CO2 with the existing minerals, form some new minerals that have carbon dioxide within their structure, or carbonate minerals, and thus freeze it in the subsurface as well. I'm not as familiar with this side of things. I know that there have been pilot projects and the BC had some very favorable geology. And Gavin, I do believe there was a carbon mineralization study by Geoscience BC. Am I correct?
Absolutely, there was, and we'll make sure we post the link to those studies on the chat. Quite an extensive amount of work done in that area as well, to complement in understanding the complex geology in BC, that there's different ways to go about this. So we'll make sure that's in the chat. Yeah, there's significant serpentinites throughout BC which are helpful to this mineralization process. So with that, I do want to say thank you again to Brad for the presentation. I know there's probably further questions, but we'll make sure to compile them and get back as best we can to the respondents and the folks that are attending here in the audience today. So with that, thank you again. And now I'd like to welcome Dr. Kathy Hickson. So Kathy is really one of the globally recognized leaders and one of Canada's foremost geothermal geoscientists, with more than 40 years of experience spanning geothermal exploration and development, operations and maintenance, as well as significant experience within the lithium sector. So today, Kathy will share insights into geothermal opportunities in BC and the important role this energy source can play in British Columbia's future energy mix. So with that, I'll turn it over to you, Dr. Kathy Hickson.
Thank you, Gavin. Lovely to be here, and hello to all the people online. I see a couple of old friends, one being Brian Fairbank, and we'll get to Brian in a minute. So let's charge ahead here. And I think, so first of all, thanks to Brad for doing a perfect segue into geothermal energy and including a nice little diagram about what we do in geothermal. But I wanted to make sure that we're all on the same page. So geothermal electricity, it actually has been produced for over 100 years. And this is the current, basically, megawatts produced. This is electricity. But I also wanted to note that Canada is not yet on this map, but we do actually have a co-produce. So this is in Alberta, Futerra Energy, where they co-produce, essentially using that hot brine that Brad was talking about it in the Swan Hills area to produce geothermal electricity. But one of the things I wanted to point out that's really important is that geothermal is base load. That's very important in today's market, where we need that base load power, and we also produce thermal energy. Okay, sorry. So there are a number of different kinds of plays, is how you would describe them in the oil and gas industry. And that is plays that are associated with particular geological environments. So what Brad was talking about in Northeast BC, these are our sedimentary basin plays, where that hot brine that he was talking about is heated up by geological forces, and we can extract that and turn that into useful energy. We also have plays that are associated with radiogenic plutons, which are hot. We also have fault-hosted systems and volcanic systems. What's important for conventional geothermal energy is heat, permeability, and the composition of the fluid. So there's sort of a little bit of not necessarily mix up, but it's hard in the world. Like you hear geothermal a lot. Well, there are different flavors of geothermal. In fact, different technologies of geothermal energy. And what I'm going to be focusing on, we call it class 2. These are conventional hydraulic systems where we are removing hot brine from the subsurface and bringing it to the surface and putting it to useful work. There are geoexchange. So geoexchange is at the low end in terms of using the earth as a battery. So we're not taking any intrinsic energy from the subsurface, but we are storing heat that we're taking from the atmosphere. And these use ground source heat pumps. We also have a growing industry in terms of what we call AGS or unconventional, EGS, so advanced geothermal systems or engineered geothermal systems. And these are, in the geothermal parlance, we would call these unconventional. We're also moving a lot more into heat capture and storage. And I want to make a point regarding that last question is that work that I've done with the University of Alberta shows that in a conventional geothermal system, we can also do carbon storage. So just wanting to add that to the value chain of geothermal. So geothermal, because of these geological controls, not all of Canada is applicable to geothermal, conventional geothermal. And that's simply because a lot of Canada is what we would call not just hot, dry rock, but dry rock and cold rock. And that's the Canadian field. And so in this diagram, what you see is a lot of basically everything in purple, we would need to employ an engineered or an advanced geothermal system. And we would also, in order to get the heat, we would need to be drilling many kilometers in depth in the order of 7 to 12 kilometers. But everything that you see in the orange is applicable to conventional geothermal systems. So this is what the map looks like for British Columbia. And this was first done actually in 1992. And that's why I mentioned Brian Fairbank. So Brian was one of the authors of this now a few decades old map, but this map has actually really proven the test of time, and we still use it today as the basis for understanding what geothermal energy is all about in British Columbia. This map was funded actually with the Geological Survey of Canada, who had a geothermal program that started in the mid-1970s and then carried through until the early or late 1980s. So in Geoscience BC, that 1992 map was based a lot on heat flow. And so what you see here in the colors is elevated heat flow relative to the rocks around it. And that heat flow is an indicator of conventional geothermal resources. So that map was updated that 1992 map was updated by Jacek Majorowicz, and he produced this new map. What you see in terms of white spaces here is simply the result of lack of data. But what you do see here in terms of the reds is, again, reflecting these areas of high heat flow. So this was part of a report that was intended to help people understand what the geothermal resource might be and where, in fact, it might be most likely to look for good resources. Then in 26, so we're going back, this map was produced in 2015 as part of that report. Then in 2016, there was a Geoscience BC produced a report, which was the economic viability, and there were 18 sites that were analyzed in this report. So this was a very good report in terms of understanding the foundation for geoscience, or the foundation for geothermal energy in these 18 sites. But I wanted to point out that this was written more than a decade ago. And I think that advances in EGS, engineered and advanced geothermal systems, might actually change this perspective. In particular, it was not anticipated the need of British Columbians for baseload power. So so Clark Lake, segue from this is one of the areas that that Brad was talking about. We know that there are hot brines in this area, and that information. So it came out in the reports that Brad talked about, but also in reports that were specific to the geothermal energy potential. And in fact, that those reports led to the development of the Tutica project up in the Clark Lake area. And Tutica is a geothermal project that uses those hot brines that are produced when you produce oil and gas, and in the same aquifers as produced in the oil and gas industry. So that work by Geoscience BC directly led to the investment and further exploration of the Tutica project. Another project that has been a long-standing project in British Columbia, in fact, one of the first geothermal projects, high temperature, was Mount Meagher. So work on Mount Meagher actually started under that federal program in the basically the mid-1970s with the drilling of temperature gradient wells, and then followed by full-size production wells. Geoscience BC funded a project in the early 2000s, and that project essentially built on the earlier technical information for the Mount Meagher project, and I think has helped that project seek additional investment dollars to move that project forward. I just wanted to do a little quick segue here for geothermal energy, and I talked about the capacity factor. And what is really important about geothermal is it provides baseload power. And baseload power is very important in terms of, I had 10 minutes. I put my alarm on and I've reached 10 minutes. So I'm just going to turn off my alarm here and continue on because I think we do have a few extra minutes. At least I hope we do. Okay, so I wanted to show this. I wanted to show this because of the importance of this capacity factor. So BC Hydro has actually let several new contracts for wind. And so this is wind in the Dawson Creek area, another one in West Kamloops, and then geothermal. So what we've done here is we've simply taken a 200 megawatt wind, calculated the capacity factor for those wind farms, and then looked at how large a geothermal development would we have, in fact, to meet the same megawatts produced as those wind farms. And they're pretty small, actually. It's a 70 megawatt in the case of the in the case of the Dawson Creek area, and 90 in the case of Kamloops. So what's really important there is to really understand what base load means. And these projects are billion-dollar projects. Geothermal doesn't have to be a billion-dollar project, and we can produce base load. Another just information here. So Lazard is a company that produces a levelized cost of power, in this case, a levelized cost of energy. And where we see renewables, sort of the unspoken truth about renewables, so these are intermittent renewables like solar and wind, is that there's a significant cost factor to essentially make them grid stable, to have them so that they will essentially be able to support a modern grid. And that modern grid essentially boosts the price up if we're talking about onshore wind with storage. The geothermal, their number that they came up with is $109 per megawatt hours. These are US dollars. By the way, is an important number that is based on conventional systems that have been working in developed areas, and those conventional systems, they're not first of kind in a region, and certainly we expect that the prices in British Columbia will be a little bit higher because these would be first in kind facilities. Okay, back on to Geoscience BC. Just did a catalog here of a number of areas that there have been specific studies. I wanted to point out the Kootenay Lake study. So this is several studies that were funded under Geoscience BC that are now hopefully leading to certainly increased interest, but in particular, increased interest that will allow them to do more exploration, because more exploration needs to get done. One of the most favorable regions of British Columbia is basically this Northwest BC area, and that Northwest BC is also Tahltan territory, and some of the largest and potentially longest lived mining activity is taking place in that area. So Geoscience BC funded a favorability assessment for that area. Note that this is relative favorability in terms of, and it shouldn't be any surprise that the relative favorability is best around the big volcanic centers. Just wanted to point out, as well as the cost and financial factors of baseload power, is that essentially we in BC need more power, and that power is best if it is stable, firm power, base load. This is just some examples of some of these new advances in geothermal technology. These are still under development. How they will end up in terms of ultimate cost per megawatt hour, we're not quite sure. So early stage exploration and resource definition is significantly helped along by government funded studies such as those supported by Geoscience BC. So I'm going to stop there.
Thank you, Kathy. Very comprehensive and very timely. So I want to thank you for that, and all the audience members will see in the chat any links to different projects that we've undertaken and completed over the many years we've been in existence. And I do want to do a quick shout out and acknowledge Carlos Salas, a former staff member that played a significant role in a lot of the energy projects that we're talking about today. So thank you to Carlos on that. So in interest of time, I may just ask a question to you, Kathy, and then I'll look for some other questions here for a minute or two. But recently we saw BC Hydro and the BC government put out a new energy plan, and in that plan it refers to geothermal. And I wanted to ask you, put you a little bit on the spot about what you think about that, given what you've just provided us now and your experience in the field.
Well, of course, I was thrilled. I mean, we've been trying to work with BC Hydro actually since the Mount Meager days in the early 1980s, where they put in a number of millions of dollars into the Mount Meager project. That project didn't go ahead at that time because I think the general financial, the energy needs of the province were different. But I think we're in a new realm. We have to increase our baseload power. We have to increase our firm power. And geothermal, as I have already mentioned, is really, other than impoundment hydro, is really the only other way to do it. So if we're talking about a renewable energy resource.
Excellent, thank you. Maybe with that, I'll again just thank you and Dr. Brad Hayes and also Resource First for sponsoring today's webinar, and Stuart Muir for your comments. Really do appreciate it. All of this is being recorded and will be provided to you at a later date. So look for that, as well as look for requests from Geoscience BC to become more involved as we go forward in the coming 2 or 3 months. we are looking for some further support, and we hope that you find these kind of projects valuable to your work and work of your companies and communities. So I do want to say thank you to everyone who was part of today's webinar and acknowledge that there's been a tremendous amount of effort and time and commitment, again, in a very collaborative model, which is quite unique and quite special. And we look forward to further discussions and support and further really interesting projects like these that you've seen today and heard about today. So with that, I'll say thank you and wish you all the best and look forward to seeing you again. This essentially concludes today's webinar. Appreciate it and thank you very much.